Hey everyone, and welcome to this explainer. Today, we're going on a seriously fascinating investigation to demystify the fundamental, invisible rules that govern everyday motion. Have you ever caught yourself wondering why things move the way they do? Or, sometimes why they absolutely refuse to budge at all? Well, we're going to build a mental toolkit to map out the unseen physical forces happening all around us every single second. So grab your focus because we are about to decode the secret language of the physical world. Here is our roadmap for today. We've got 1. The magic of inertia, 2. Contact and non-contact forces, 3. The friction factor, 4. Free body diagrams explained, and finally, 5. The balancing act. Section 1. The magic of inertia, setting the stage. Okay, let's dive into this. I want you to picture a classic magic trick in your head, the famous tablecloth trick. Imagine a fully set dining table. A magician grabs the edges of the tablecloth and gives it a really rapid, sharp yank. The cloth flies out, but miraculously the plates, the glasses, the heavy coins sitting right in the middle, they all stay perfectly put. Our immediate question as investigators here is, what just happened? Why on earth didn't the objects fly off the table with the cloth? Well, the answer to that mystery isn't magic at all. It's physics. And to solve it, we turn to the ultimate physics detective, Sir Isaac Newton. Way back in the 17th century, he laid out the principles of dynamics that we literally still use today. His first law of motion provides the exact theoretical toolkit we need to explain why that dinner plate or coin completely ignored the violently moving tablecloth. It all comes down to something called inertial frames of reference. In simple terms, this is a framework where Newton's first law holds entirely true. An object at rest stays at rest unless acted upon by an outside force. That coin on the table, it has inertia. Think of inertia as a natural stubbornness to change. The tablecloth was pulled so incredibly quickly that friction just couldn't overcome the coin's inertia, so it stayed exactly where it was. Moving on to Section 2, contact and non-contact forces, pushes, pulls, and beyond. Before we analyze specific forces, we really need to know what a force actually is, right? At its most basic level, a force is simply a push or a pull. It's always an interaction between two objects or between an object and its environment. And crucially, this is a big one, a force is a vector quantity. That just means it doesn't only have a size or magnitude, it also has a specific direction. You don't just push, you push towards something. And this brilliantly illustrates how we actually map this stuff out. In physics, we map these pushes and pulls using arrows. The length of the arrow tells us the magnitude, basically how strong the force is, and the way the arrowhead points tells us the direction. Whether a hand is pushing a block or a string is pulling it, mapping out these directional arrows is the absolute first step in solving any motion problem. Now, we can divide all these pushes and pulls into two main categories, contact forces and non-contact forces. Contact forces require actual physical touch. Think of the tension in a rope, the normal force of the ground pushing up on your shoes, or the fluid resistance of water pushing against a swimmer. Non-contact forces, on the other hand, are action at a distance. They operate without any physical connection whatsoever, like the gravitational force pulling that coin down toward the earth, or the pull of magnetic forces. Section 3, the friction factor, static versus kinetic. Now, what's really interesting about this slide is that friction actually has two totally distinct personalities, static and kinetic. Static friction is that stubborn force holding an object at rest. It's like when you try to push a massive fridge and it just doesn't budge. But once you push hard enough to break that maximum static threshold, kinetic friction takes over, acting against the moving object. Interestingly enough, kinetic friction is actually weaker than static friction, and it stays relatively constant the whole time the object slides. To really visualize kinetic friction, picture a sled sliding down a snowy hill. Once that sled is in motion, kinetic friction is the constant force acting in the exact opposite direction of the sled's movement. It's the drag between the runners of the sled and the snow. If you've ever noticed that it's way harder to start dragging a sled than it is to keep dragging it once it's moving, well, you've experienced the exact difference between static and kinetic friction firsthand. Which brings us to Section 4. Free body diagrams explained, visualizing the invisible. Constructing a free body diagram, or an FBD for short, is a beautifully systematic problem-solving strategy. It's like a puzzle, and the rules are super simple. Step 1. Draw the object you're studying. And seriously, don't worry. It doesn't have to be artistic. A simple dot or a box is totally fine. Step 2. Draw arrows to represent only the external forces acting on that specific body. You completely ignore everything else in the environment. This isolates the object so we can see exactly what invisible hands are pushing or pulling it. Let's look at a real-world example here. This is a free body diagram of a scuba diver. Pointing straight down is the diver's weight. That's a non-contact force from gravity. Countering that, pointing straight up, is the buoyancy force exerted by the water. Then, kicking causes the water to exert a forward reaction force. That's our thrust pointing left. And finally, acting against that forward motion is the drag force from the water, pointing to the right. 4 distinct external forces dictating exactly how this diver moves through the water. Let's move to and see how this builds in a slightly more explosive scenario, a sprinter exploding out of the starting blocks. Alongside the downward weight vector, the force of the starting block pushes on the runner at a sharp angle. We can actually break that angled force down into 2 components: a vertical upward component that counteracts the sprinter's weight, and a massive horizontal component that provides the intense acceleration forward down the track. And, we can't really talk about forces without highlighting Newton's third law, action-reaction pairs. To go up, a jumping basketball player must push down against the floor. The floor then pushes back up with an equal and opposite reaction force, which perfectly maps to the normal force vector. By pushing down hard, the player increases the upward reaction force of the floor, propelling them high into the air to make the shot. It's a perfect illustration of how analyzing external forces reveals the true mechanics of human movement. Section 5. The Balancing Act, Equilibrium and Newton's Laws.
So the crucial point is this concept right here, equilibrium. Once we've drawn an accurate free body diagram, we look at all the zeros we just made. If the forces pulling left perfectly cancel out the forces pulling right, and the forces pushing up perfectly cancel the forces pulling down. The net external force is 0. We write this out as F net equals 0. When this happens, the body is in equilibrium. This means Newton's first law applies perfectly. If it's at rest, it stays at rest. If it's moving, it just keeps right on moving at a constant, steady velocity.
But hey, what happens when the arrows don't cancel out? Like when the thrust is way bigger than the drag, or gravity is much stronger than the normal force? Well, if those forces are unbalanced, meaning F net is not 0, the object definitely cannot stay in equilibrium. Instead, it's going to accelerate in the direction of the net force. This actually takes us right to the doorstep of Newton's second law, which explains exactly how that acceleration happens. But actually, that is a thrilling topic for another time. We've covered some truly incredible ground today, from the stubborn magic of inertia to the intricate mapping of a free body diagram. I want to leave you with this final, somewhat provocative thought. After drawing free body diagrams and learning about Newton's first law, how do you now see the role of forces in keeping objects at rest or in motion? The next time you sit in a chair, push a heavy grocery cart, or watch a basketball game, try drawing those invisible arrows in your mind. The physical world is constantly speaking the language of forces, and now you know exactly how to translate it. Thanks so much for joining me on this explainer, and keep learning.